All right, so a couple weeks ago, when we talked about different states of matter, we looked at different ways of organizing matter, pure substances and mixtures. And then pure substances we broke down more into elements and compounds. In the last chapter, we really focused on elements and what they're made out of and how to count all these particles. Now we're going to build that up and talk about compounds in a little bit more detail. So if you recall, when we talked about compounds, one of the things that we said about them is that they have more than one element chemically bound together. So in compounds, the atoms are connected by chemical bonds. But we didn't really define what that means. We talked about chemical changes and chemical reactions, but we didn't really define specifically what a chemical bond is. And it's actually kind of a little bit of a hard thing to define exactly what it is, because it actually encompasses a couple different things. So we're going to talk about two different styles of chemical bonds that you've probably heard of before. What have you heard of? What kind of chemical bonds have you heard of before? Covalent is one. Ionic is another, yeah. We're going to look at those two. They're very, very different in terms of how they work and how they make compounds. So let's talk about the covalent model first. We're going to do a whole chapter on covalent compounds and bonds and how to kind of build that stuff together. But basically, a way that we can define a covalent bond is that two atoms are close enough so their electrons can occupy orbitals in both atoms. So this is sometimes referred to as shared electrons. But we talked about how the electrons are outside in these orbitals outside of the nucleus. So if two atoms get close enough together, those electrons actually end up occupying those orbitals in both atoms at the same time. And for some compounds, that leads to a special stability that we'll get into in later chapters. Now here's where I'm going to actually deviate from the book a little bit. I think the book's got it a little bit wrong. There are actually two types of covalently bound compounds. There are molecules, and the book kind of conflates this and says that all covalent compounds are molecules, and that's not true. So yeah, the book says we call covalently bounded compounds molecular compounds, and we can do that sometimes, but there is a difference. A molecule is a discrete piece meaning that the atoms are covalently bound together and it has boundaries. This is part of the molecule, and then the molecule ends. So something like water, if we draw it like that, water has some hydrogen and oxygen bound by covalent bonds, which are what those lines represent. And those are, and that's it. That's the whole molecule. It's not then also covalently bound to other stuff. It has kind of boundaries. So you can say this thing is just one water molecule. But there's another type of covalent compounds that the book doesn't really discuss until a later chapter, called covalent solids. And we're going to put this in quotes here. would say that it's extended infinitely. It's not truly infinite from like a mathematical perspective, because of course there are boundaries on reality. But if you take something like a diamond, for instance, diamond is made of carbon. But, and you don't have to try to draw this if you don't want to. So diamond is covalently bound carbon. That kind of looks like this. So it's this kind of three-dimensional structure, and it doesn't just stop at what I've drawn there. Those lines that are extending out continue out to make that same structure over and over again. Oops, there's one here too. Back there. Each carbon needs 4 bonds, and so this continues to extend on and on in that same pattern. So that's still a covalent compound. Those are covalent bonds between the carbons, but it's not a single molecule. Eventually it will end, because you can have a discrete diamond, but only when you have, whatever ridiculous power of 10 number of carbons. So it's essentially infinite. So that's 2 types of covalent molecules. Diamond is one example. Another example would be quartz or silica, which is what most rocks, most of the Earth's crust is made out of. That's again SiO2, silicon dioxide, and that is an extended solid made of covalent bonds between silicon and oxygen, but not a discrete molecule. All right. That's all we're going to say about covalent stuff for now. We're going to spend a little bit more time today on ionic compounds. Ionic compounds are a bit simpler than covalent compounds because they're formed simply by attraction of positive and negative charges. So cations and anions. Sometimes we talk about ionic compounds as coming from giving up, one atom or one element gives up its electron to another one. And that's true in some cases, but in a more general standpoint, that's not always going to be the case. But more generally, ionic compounds are always just an attraction between positive and negative. So if you've taken physics, you might have talked about this stuff a little bit. This is called the Coulomb or Coulombic force. It has an equation similar to the gravity equation that just says that positive and negative charges attract each other with this particular force. And that's what holds these compounds together. It's how tightly the positive and negative ions can kind of pack together. So ionic compounds are not covalent. They're not sharing the electrons, and we don't express ionic compounds with lines. The lines like we did in the water and the carbon there, those lines are reserved only for covalent compounds. So we generally express ionic compounds just by their formula unit. So something like NaCl, right, is an ionic compound made from sodium ions, sodium cations, and chloride anions. We would call that a formula unit, which is very different from a molecular formula. In a molecule, we can say specifically this is the number of atoms that are all connected together for one molecule. H2O means 2 hydrogens and 1 oxygen in a molecule. We can also have H2O2, which is hydrogen peroxide. That is not a formula unit because it's not reduced, but it tells us there's 2 hydrogens and 2 oxygens in that molecule. For an ionic compound, we always just reduce the numbers as low as possible to just make a ratio. So NaCl does not mean 1 sodium atom connected with 1 chloride atom in a molecule. It means we have this large ionic compound where there are sodium cations and chloride anions, and there's a ratio of 1 to 1. For every sodium cation, there's a chloride anion. So how can we know that it's a ratio of 1 to 1? Like, let's say you didn't know the formula for sodium chloride. How could you figure it out? Why does it have to be a 1 to 1 ratio? Any idea?
Because there is no small number.
What?
There is no small number, like in H2.
That's right, but how do we know that there isn't supposed to be? Like, how do we know the ratio isn't supposed to be like 2 sodiums to 1 chloride or something? Okay, so how?
Number of protons and electrons.
Yeah, we can look at the charges. So ionic compounds wait a minute, there we go. Ionic compounds generally are neutral overall. That's not 100% true 100% of the time, but for what we're going to see, that's a good rule of thumb. So to find a formula for an ionic compound, you have to know the charges of the cation and the anion. So let's practice that. So if we want to find the formula of an ionic compound, we first need the charges of the cation and the anion. Okay. So let's say we want to write down a formula for potassium oxide. So the first step is let's find the charges of the cation and the anion. So how do we do that? How can we figure out what charge potassium should have as an ion? So everybody's looking at the periodic table, which is good. That's exactly right. What information do you get from the periodic table on that regard? Right, so we remember from last week that there are certain areas of the periodic table where the charges are very predictable. They always make the same charge. And one of those areas is column 1A. So all of the elements in column 1A generally make +1 cations. So from knowing that, we can say, okay, we know that potassium is a +1 cation. If you didn't know that, go back and review that chart. We're going to use that same information to find the charge of oxide. Anybody remember what charge oxygen makes? Yeah. Minus. Close. -2, yeah. So one way to remember that is if you remember that there's +1 over here, you go to the other side of the periodic table, the noble charges are 0, or the noble gases are 0 charge. Then going to the left from there is -1, -2, -3. All right, so the halogen's -1, the oxygen would then be -2. So oxide is -2. And our first step is done. So then all that leaves is the second step, which is adjust ratios to neutralize the charge. So we've got K plus and O2 minus. If we put those together and just make this KO, what's wrong with that? It's not neutral because we got more minus than plus. We have 2 minus, 1 plus. So if we put those together 1 to 1, there's still too much minus. So what do we do instead? Yeah, we need another K. So now we've got 2 plus total and 2 minus total. So together that's 2 plus, and that's 2 minus. So that's 2 plus, 2 minus, that's neutral. And then we can write down that formula. And the way that we express that ratio is using a subscript 2 on the K to show that we need 2 potassiums for every 1 oxide. All right. Good so far? Great. So let's try another one. You do this one. Oops. I'll give you 2 of them to do. All right, so see if you can find formulas for those 2 compounds, ionic compounds, using that technique. Ready to find some formulas? Let's go through the steps here for the first one. So we look up calcium in row 2A. What's its charge? 2 plus, yep. And then nitride? 3 minus, good. So how do we bring those into balance? Yeah. Yeah, since 2 and 3, we can't just change one of them. We have to actually change the numbers of both of them to find a common factor, or a common multiple. So if we add 2 more of these and 1 more of that, that gives us a 6 plus and a 6 minus. And then those are neutral. So that overall compound can be written as Ca3N2. Okay, good. What about aluminum chloride? Let's go for that one. Yeah, AlCl3. So we know aluminum is plus 3, chloride is minus 1. So we need 3 of those so that the charges balance out. And that gives us AlCl3. Great. Yeah.
Did you just take like the exponent and like switch it and get like the set number?
Most of the time. So that mostly works. Yes. So the question is, if you know something is 2 plus and you know something is 3 minus, you can put the 2 becomes the subscript on the one that's 3, and the 3 becomes the subscript on the one that's 2. You see that? how that kind of works? That mostly works. Same thing over here. You've got your 3 from the aluminum that goes to the chloride, and the 1 from the chloride that goes to the aluminum. Where that doesn't work is when you have charges that reduce. So let's say you had a 4 and a 2. You'd want 2 of the 2 and 1 of the 4, not 4 of the 2 and 2 of the 4. You see what I'm saying with that? So in that case, you'd have to reduce it when there's larger numbers. But for the smaller numbers, yes, that works. Thanks. All right. So what happens with all of the other compound or all of the other elements that you may not know what the charge is? Like, let's say we have iron or something. Any idea what we do with that? Which is Fe right in the middle. Not one of the ones with a predictable charge. Yeah, exactly. So all those ones in the middle have multiple different charges. That's why they didn't appear on that chart of predictable charges. Iron can be +2 or +3. There's a lot of them like that. Copper can be +1 or +2. Lead can be +2 or +4. So there's a lot of different possible variation there. So to deal with that, we actually need to be given that information to find the compound. Telling somebody iron chloride is not enough information to be able to write down a compound. So instead, that compound is written like this. For any of the for any of the elements that make multiple different charges, and this only happens with cations, with positively charged ions. This charge is actually specified in parentheses after the name. So that 3 tells us that there is a +3 charge on iron. And it's always written in Roman numerals and parentheses right after the name of the cation. The confusing part about that is, so we would say that name as iron 3 chloride, specifying that this is iron +3. But everybody always wants to make that 3 into the subscript on iron, and that's not what it is. It's the charge, not the subscript. Okay, that's the charge. So our compound ends up being FeCl3 because chloride is -1, and so we need to neutralize that charge. We'll get into more about how that's used in a little bit when we talk about the naming rules. Questions about that? Okay. There are some older names, too, that you'll encounter in some of the book and some of the homework, but you don't have to know them. If you've heard, this compound often goes by another name. I don't know if anybody's heard it, ferric chloride. In an older way of specifying like the difference in the two charges between iron 3 and iron 2 was to call one ferric and one ferrous. And so you may have heard those kinds of terms before. We're not going to use those names because they're no longer considered, I mean, they're still around, but they're no longer really considered correct because this helps us out so much more. To know what ferric chloride is, you have to know what ferric means. To know iron 3 chloride, you just have to know like that the parentheses tell you the charge. So it gives you more information, makes you have to memorize less stuff in terms of names. So that's the way that we use it. All right, that only, as I said, it only applies to the cations. So, we're good so far? All right. The other type of ions and the other types of names that you run into are the polyatomic ions. Which are ions made from covalently bound atoms. So things like hydroxide, OH-, or nitrate, NO3-, or sulfate, SO4 2-. Hopefully you've had to memorize most of those in a previous class, previous chemistry class. You probably had some sort of a chart that you needed to memorize. Well, guess what? You get to refresh your memory and get all those back again. I'm going to put a chart in here for you on our notes. Okay. We're going to get, whoa, I got a little big. We're going to get to practice this in one of the labs too. Okay. So there are some of the polyatomic ions. Hopefully you know most of those. The drawback, or not the drawback, the thing that can be difficult about polyatomic ions is there's really not a good way, at least until we get a whole lot more information later in the semester, to figure out what the formula and the charge should be. You really just have to memorize it. So you should know at least for that list, and hopefully a few other ones, but at least make sure you know that list. From that list, you can usually figure out the other ones that you need. Make sure you know the name, the formula, and the charge for all of those. All right, so make yourself some flashcards, get an app or something, and commit all of those to memory. Because there's really no other way to figure that out. You need to know if it's potassium nitrate, you need to know that potassium is +1, nitrate is NO3 -1, so the formula is KNO3. Potassium sulfate, you need to know that sulfate is SO4 2-, and so then the formula would be K2SO4. So with these, they're all made from more than one atom covalently bound together. The only cation in the list is ammonium down in the lower left. The rest are all anions. People like to memorize these in different ways. Some people just, you just do flashcards or something. Other people like to organize it a little bit more and look for some patterns. Maybe like put all the 1- anions in a category and the 2- and the 3- or something like that. Arrange it how you see fit, but you will need to have these down by the next quiz, which probably will not be next Tuesday because we'll need a little bit more time. It'll probably be the week, either the week after or next Thursday. We'll see how far we get on Thursday. Okay, so let's start taking a look at some names. Now we know how to write compounds from, write the formulas from the names. Like if I gave you a name, you write down the formula. But we want to be able to go the other direction too. The other direction's a little bit harder because you have to know some different rules. So to name ionic compounds, the first thing you have to do is decide if it fits into one of two categories, kind of like when we were sorting matter. You need to decide if it is what we call type 1 and what the book calls type 1, or type 2. These are not important designations. There's just two different types. Type 1 are all of the compounds with a predictable cation charge. So that's like what we talked about. All of the ions where you know the charge just from the name because there's only one choice. So column 1A, cations. Column 2A, cations. Aluminum, which we know is 3+. We're going to add three more to the list here that are, you can't figure it out based on the position in the periodic table, but you can know it just because it's always the same. So that would be zinc, which is always +2, cadmium, which is always +2, and silver, which is always +1. In addition, this category also includes any polyatomic cations, which for us, the only one we're really going to encounter is ammonium. So these are all the ions where you know the cation charge just from the name. If I say magnesium, you can look at the periodic table and go, oh yeah, that's got to be +2. If I say rubidium, you can look that up on the periodic table and say, oh yeah, it's got to be +1. If I say silver, you can't look it up on the periodic table, but you know it's got to be +1. Okay, so that's the predictable charges. And then type 2 are the unpredictable charges, or we'll just say variable charges. Which is anything not in that list that we just made. So all the transition elements, and then some of the main group metals that are below the stair step, things like tin and lead and thallium, and that have different possible variable charges. So they might be +2, +3, +4, +5, whatever, depending on the element. Okay, so let's look at the two different rules. So for type 1s, the way that you name it is you just say the cation, and then the anion, which in most cases changes the end of its name to I if it's a simple monoatomic anion. Otherwise, it's just the name of the polyatomic anion. So this would be things like what we saw, like potassium chloride. It's not chlorine, it's chloride because it's an anion. Calcium sulfide, magnesium oxide, all of that kind of stuff. Just a simple name, you just say the cation, you say the anion. The other category type are type 2 compounds. Same basic setup, but you got to put the charge of the cation in parentheses. And of course, for polyatomics, that I doesn't apply. Like nitrate is just nitrate. But for simple single monoatomic anions, then you'd use that I. All right, so that's not too bad. The only difference in the two types of names is whether or not you include the charge. So let's try a couple. Okay, let's look at that first one. So, first question should always be, which category does this go in? Is the charge on the metal, on the cation, is it something that we just know, or could it be some different ones? So what do you think for that first one? Do we know the charge or not? We do, because it's in 1A. And all ones in 1A, we know the charge. So what is the charge, incidentally, on potassium? +1, right? Okay, so that tells us for sure that this is type 1, meaning no parentheses. Okay, so let's write that name. It starts with potassium. And what's the anion? Somebody said it. Go ahead. Close. That phosphorus is the element. What is that anion called? Nope. Close though. Anybody else?
Phosphate.
It's phosphate. So this is a polyatomic anion. So this is one that you need to know from the list, right? It would be right here, phosphate. And that's it. That's the whole name. Okay. Next one. Is it a known, which category do we put it in? Do we know the charge or not necessarily? We don't, because it's copper right in the middle. So this is going to be type 2. Okay. So that means that we're going to need those parentheses. So our anion, or our cation, is still going to be called copper. But we have to figure out what charge we're going to put in parentheses there. And we'll do that in a second. What's the anion called here? Yeah, so phosphate was PO4. If it's just a single element, just like chlorine or oxygen or whatever, we cut off the end and we put "ide." So this becomes phosphide. So now we have to figure out the charge on copper. How do we do that?
Isn't it the same number as the subscript?
It's not. No, it's not the same number as the subscript. But you're on the right track. We're going to use the subscripts to figure it out. Yeah, we have to use the charge on phosphide. We know the charge on phosphide because we know that that's in column 5A with nitrogen, and so we would predict that it has a -3 charge. So we know that's a -3 charge, and we know from the formula that there are 2 of them because it's Cu3P2. So that means that if we have 3 coppers, we want to answer the question, what does the charge on each copper have to be so that the overall charge of the compound is neutral? So what does the charge on copper have to be to make it all neutral? 2, right, plus 2. So that tells us that this is copper 2 phosphide. Okay, let's try another one. Got 2 more minutes here. All right, you try this one. See if you can write down that name. And then I'll tell you. All right, anybody think they got a name for this one? Give it a try.
Is it strontium nitrate?
Is it strontium nitrate? What do you think? Agree? Disagree? Yeah? Yeah? Maybe? No? Yes, that's correct. Strontium nitrate. So in this case, it's a type 1 because we know strontium is always plus 2, so we don't have to put the parentheses. And then we know from the chart that NO3 is nitrate. In this case, because it was type 1, we don't have to worry about figuring out charges or anything like that. So this is just strontium nitrate. All right, so please get to work on these. Get memorizing and get practicing. The mastering chemistry should be the beginning of your practice or part of your practice, but you should be doing a lot more than that, either through the textbook or whatever other kinds of resources you're using. Let me know if you need some guidance in that way. But please get practicing on this so that you can do these names. And so tomorrow's lab does not have any hazardous substances, so you don't need to look anything up for that. Oh, we're about out of time. I believe it does have a some pre-lab questions. So there is a document in Blackboard there that says pre-lab. So please, as part of your pre-lab preparation, either in your notebook or on separate paper, just answer these 5 questions before tomorrow. And I'll see you in the morning.